So we know that if we have a function f and we want to find the slope of the tangent line at, say, this point P right here, we can do that by defining some coordinates. We can say that maybe this is A, and then this is f of A, and then maybe we could call the x-coordinate of another point, say point Q, we could call that A plus H, so that this distance here is H. And then this would make the y-coordinate of point Q f of A plus H. And then the slope of the tangent line is the limit as h goes to 0 of f of A plus H minus f of A over H. This was the alternate expression that we had for the slope of the tangent line. We also had another expression where instead of A and A plus H, we were using A and X, and we had f of A and f of X. So either one will give you the slope of the tangent line. Now let's look at a similar situation, except this time let's look at this thing S here, which is displacement. And we're going to plot displacement over time for a particle. So displacement is a physics term. If you've ever taken a physics class, you've probably heard of displacement. It's a vector, means it has both a magnitude and a direction. And you can think of it as the position of the particle as measured from the origin, the displacement from the origin. So we'll look at this in a little more detail later on, but for right now, just notice that this looks exactly the same as the situation we had before. And so if we wanted to find the tangent line at this point P right here, we could do a very similar thing. We could actually use the same notation. I can call this A, and then I can call this A plus H, and I can call this f of A, and I can call this f of A plus H, our y-coordinate here. And so we get something that looks exactly the same. And what we're actually finding here is the velocity, the instantaneous velocity at point A, by letting the limit as h goes to 0 of f of A plus H minus f of A over H. So we can see that what we've already done, finding the slope of the tangent line, also allows us to find instantaneous velocity. So let's look at this in a little more detail. So we're going to consider a particle moving along a straight line. And I've just created a graph here for a displacement versus time for this particle, and I'm just using arbitrary units for now. The point is just to understand what this graph means. So let's define the variables first. S is the displacement measured from the origin, t is the time, and f is the position function. So this is our position function that we have graphed here. So let's try and understand what's going on. Remember, this is a particle moving along a straight line. So here is our straight line. This is the s-axis here. And let's look at what's happening over time. So we see that at time 0, remember this is the time axis, we're at -1. So we're starting right here. So at this point right here, which I'll call point A, this is where we're at. Then at time t equals 1, our position is 0. So we've moved to here at point B. Then at time t equals 2, at point C, we're at a position of 3, so we've moved over here. There's point C. And then at time t equals 3, we're all the way up here at 8. And I'll call that point D, and so at point D, we're over here. So you can see we went from A to B, and then B to C, and C to D. And each of these intervals between A and B, B and C and D is 1 unit of time here. Maybe if you think of this as seconds, then that would be 1 second in between each letter here. So if it's 1 second from A to B, another second from B to C, and another second from C to D, you can see that the particle appears to be speeding up. Okay, so now that we understand how to read a graph like this, let's look at how we might find velocity. So here's the graph that we saw in the beginning. This is our S versus T, displacement versus time. And again, we will define some variables here. We'll say that this point P has a coordinate of A, and that this point Q has a coordinate of A plus H. And then I won't write it again, but we have f of A and f of A plus H over here for the y-coordinates. And so the average velocity, that's actually the same thing as the slope of the secant line. That was f of A plus H minus f of A all over H. If we want the instantaneous velocity, the velocity right at point P, which sometimes people just call it plain old velocity, then that is the limit as h approaches 0 of f of a plus h minus f of a over h. And I want to point out that average velocity is something that you compute over an interval of time. We would ask about the average velocity from this time here to this time here over this time interval. While instantaneous velocity, that's the velocity at a point, at point P, in fact, for what I have here in the diagram. So average velocity interval, instantaneous velocity is at a point. So let's look at an example of how we might use this idea. So let's suppose the position function for a particle is given by s equals f of t, which equals 3t squared minus 5t plus 6, where s is in meters and t is in seconds. And by the way, sometimes you'll see this part here, this s equaling f of t. Some people will just shorten that to be s of t, or displacement as a function of time. And so the first question we want to ask is, what is the average velocity from t equals 2 seconds to t equals 4 seconds? Notice it's average velocity, and so it's asking about a time interval. So to calculate average velocity, remember the formula was the same thing that we had for the slope of the secant line. So the average velocity is going to be f of 4 minus f of 2 over 4 minus 2. This was the original formula that I had. You can also look at the a plus h formula. In this case, our h is 2. It's the distance between 2 and 4 would be 2. And our a is 2, and 2 plus 2 is 4. That's what gives that 4 right there. But either formula works, so now we just have to plug in here. So f of 4, so that's going to be 3 times 4 squared minus 5 times 4 plus 6. And then that whole thing minus f of 2, which is going to be 3 times 2 squared minus 5 times 2 plus 6. And then all of that is going to be divided by 4 minus 2, which is 2. And so now it's just a lot of arithmetic here. So this is 3 times 16 minus 20 plus 6 minus 3 times 4. And then this will be plus now. Plus 10 and minus 6, and this is all going to be over 2. Our plus 6 and our minus 6 can go away, and so we're left with 3 times 16, that's 48. So we have 48 minus 20 minus 12 plus 10 all over 2. And so if we compute all this, we end up getting 26 over 2, which is 13, and the units will be meters per second. You'll notice that velocities will have units of meters per second if we're talking about our standard units of meters and seconds. If we're talking about, say, feet and seconds, and it'll be feet per second, it will always be some kind of a length over some kind of a time. Okay, let's look at another example now. How about the instantaneous velocity at t equals 3? So to find instantaneous velocity, that's v of 3, that's the velocity at 3, and that was the limit. So this is the limit now as h approaches 0 of, and this the formula was f of a plus h. I guess I'll write it out here, f of a plus h minus f of a all over h. And so the question here is, what is a? And we can see that in this case a is going to be 3, and so this is going to be the limit as h approaches 0 of, so we have f of 3 plus h, or h plus 3. That's going to be 3 times h plus 3 squared minus 5 times h plus 3 plus 6, and then this whole thing minus, and I recommend putting the brackets around this so that you really remember to distribute that minus sign right there. This is where a lot of students make mistakes here, is forgetting to distribute this. And so this is going to be 3 times 3 squared minus 5 times 3 plus 6 all over h. Okay, so I'm going to write the limit here, and then I'm going to pull that h 1 over h outside so I don't have to worry about it. And just look at the numerator here. So I have 3 times h plus 3 squared. Well, it's going to be h squared plus 6h plus 9 when I square that out, minus 5h minus 15 plus 6, minus, and then I have 3 squared, that's 9. 9 times 3 is going to be 27, plus 15 minus 6. And let's see, I have a plus 6 and a minus 6, and I have a minus 15 and a plus 15. Those are going to cancel. And so I have the limit as h approaches 0 of 1 over h times, and then I'm going to have 3h squared plus 18h plus 27 minus 5h minus 27. And the 27s will go away. Now I have an h in every term, so I can divide out an h here. And so I'm going to get the limit as h approaches 0 of, and what will I have left here? I'll have a 3h plus an 18 minus 5 once I divide out the h's. And then if I let h go to 0, this is just 18 minus 5. So my final answer for this is 13 meters per second. And that's for my instantaneous velocity at t equals 3. I know we had 13 meters per second for the average velocity in the previous part, and that was just a coincidence here. But in this case, we're doing the limit, so we're really finding the slope of the tangent line graphically. Let's look at one more question here. How fast is the particle traveling when the displacement of the particle is 4 meters? So when the displacement is 4 meters, that's setting this s here to 4. So remember, this s is the displacement. So that would mean 4 is going to equal 3t squared minus 5t plus 6. And so this is a quadratic. I'll rewrite it in standard form by subtracting the 4 over here. So I get something that looks like this. This can factor. And so we can do quadratic formula or complete the square, or if you happen to see how it factors, I'm just going to go ahead and do it. So this is going to be t minus 1, and then the other factor is going to be 3t minus 2. That tells us that either t equals 1 second or t equals 2/3 seconds. So I actually have 2 times when the displacement is 4 meters. So we actually then want to find v of 1 and v of 2/3. So to find v of 1 and to find v of 2/3, it actually maybe helps, since we have to do this twice, to actually find v of a in general, and then we'll just plug in for a later on. So this is the limit as h approaches 0 of, and I'm going to put the 1 over h right out front in the beginning here. So this is going to be f of a plus h minus f of a. So this is 3 of a plus h squared minus 5 of a plus h plus 6. And that's this whole thing here. Let's put parentheses around it, minus, and then I'm going to have 3a squared minus 5a plus 6. Okay, so this is going to look very similar to what we just did. So I'm going to kind of go through it quickly here. So now I can multiply this out here. So I'm going to get 3 times a squared plus 2ah plus h squared. And this is going to be minus 5a minus 5h plus 6 minus 3a squared plus 5a minus 6. And then I have some 5a's canceling. I have a 6 canceling here. I'm going to have a 3a squared here and a minus 3a squared here. Those are actually going to cancel as well. And so I have the limit as h approaches 0 of 1 over h. And let's see here, I have 2ah plus, this is going to be, 6, because I have a 3 multiplying it. 6ah plus 3h squared minus 5h. And I can cancel one of the h's out. So I'm going to get the limit as h approaches 0 of 6a plus 3h minus 5. And now I can let h go to 0 and end up getting 6a minus 5. Okay, so that's what this is in general. And now I can plug in for v of 1. So v of 1 is going to be 6 times 1 minus 5. And 6 times 1 minus 5 is going to give me 1 meter per second. And I can also find v of 2/3. So that's going to be 6 times 2/3 minus 5. And when you calculate that, you end up getting negative 1 meters per second. Notice that velocity can be positive or negative. Velocity is a vector, has a magnitude and a direction, so it's allowed to have a direction here. And when we have a positive one, it generally means we're moving in the positive direction on the x-axis or the s-axis. And we have a negative one means we're generally moving in the negative direction on the s-axis.